So now let's understand the modified quicksort algorithm. This modification was proposed by Sedgewick, and I'll also provide a reference link below this video from Wikipedia, which actually explains this algorithm and the source of this algorithm, and cites Sedgwick's work as one of the pivotal movements which made this modified quicksort algorithm. And the objective of this, let's be very clear here. So in the previous video, we have seen that if you use the simple CLRS implementation of quicksort that we discussed earlier, in the worst case, we could get a space complexity of theta of n. That too, when the whole array is already sorted. If the array is already sorted, we could get a theta of n worst case space complexity, right? Because of the call stack. We have seen this. Now what we will do here is we will modify. The objective here is to modify the CLRS recursion, the CLRS recursion based simple quicksort that we have seen, recursion based quicksort that we have seen, and modified such that its worst case space complexity is theta of log n, right? And it's a very innovative algorithm, and here is the actual algorithm itself. I'll walk you through step by step. Okay, so let's take an example. Actually, let's start with the example that we saw earlier, right? Let's start with this already sorted array. Imagine I have a sorted array like this, right? Let's start with the same example that we used in the previous video. 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? This is 1, this is 9. So what happens in my very first call, I will basically call Q A, P equals to 1, R equals to 9. So here is your program, right? Here is your program. We'll go step by step and understand this, right? So now while this is happening, first I check. So here the interesting thing is I have both recursion and iteration. Look at this. This is basically iteration for me. This line, if you notice, this line, while P less than R, right? This line indicates, so in this algorithm, I have both iteration and recursion. I have both of them, right? Because if you notice here, I'm calling quicksort here and I'm calling quicksort here also. So I have both an iterative loop and a recursive loop. This is a very, very innovative. While it's just 9 lines of code, it's a very, very innovative algorithm. So let's see why it's innovative, right? So while doing this, what happens? This becomes my pivot element. So it says while P less than R. Yes, P is less than R. So we go into this while loop here, right? We go into this while loop. So what's happening within this while loop? Q equals to partition APR. So what happens to Q now? While this algorithm is running, this is my pivot element and this is the largest element because this is already a sorted array, right? So my Q will become equal to 9, right? Now it checks two things. Let's see what it checks. It checks. So if you look at this, this becomes my Q also. This is already my R. This is my P. So if you notice, it's checking two things. It's checking Q minus P and R minus Q. If you think about it, imagine if you have an array like this. Your first element is here. Your last element is here. And let's assume your pivot element was moved here, right? So what it's checking is Q minus P is basically this length, right? R minus Q is basically this length. So it is checking which part of it is smaller, right? So what this line, if Q minus P is less than R minus Q, right? What does this mean? This means if this part is smaller, if this part of the array is smaller than this part, and if this part is larger, right? If this part is smaller, then what does it say? It says quicksort on this part. It says quicksort on. So the core of this algorithm is, first it finds the partition, then it checks which part, because your pivot element here breaks the array into two subparts, right? This part and this part, the left part and the right array. If your left array is smaller than your right array, and that I can check by simply comparing Q minus P and R minus Q, right? Because Q is where your pivot element ended up, right? So Q minus P gives me the length of the left array. R minus Q gives me the length of the right array. So it's saying if the left array is smaller than right array, That's what it's saying, right? If the left array is smaller than the right array, then perform the quicksort on the left subarray, because p and q minus 1, this is q minus 1, this is q, and this is q plus 1, right? So if the left subarray is smaller, then perform the quicksort on this subarray. If the right array, so else, there is also this else condition. Look at this quicksort line. So we saw this quicksort line and this quicksort line in the previous algorithm also. So if you look at this, if you look at the previous algorithm, we had both of them. So what were we doing in the previous case, in the CLRS algorithm? We would find the partition element, and first we would perform quicksort on the left part, and then we would perform quicksort on the right part. That's what we were doing. While in Sedgewick's modified algorithm, what are we doing? We are first performing, this is the key element, right? This is a key idea. First we perform recursion. So we recurse on the smaller subarray first, and then we recurse on the larger subarray. Or sorry, we only recurse on the smaller subarray. We don't recurse on the larger subarray. We first finish the recursion on the smaller subarray and let this loop continue. Right? This is where the innovation is. Okay, let's see. You'll understand it better when we run it through this example. Right? So what happens now? Let's compare. So what do we have? We have P here, Q here, and R here. So what happens now? If you think about it, this is like the worst case breakup of my array, because this is my left subarray now. This is my left subarray. This is my right subarray. My right subarray is of length 0. Right? My left subarray is of size n-1 now. So first it will try and process the right subarray, because I don't have a right subarray. Right? So first let's see. First I'll compare Q minus P. What is Q minus P? 9 minus 1, which is 8. This is my Q minus P. And I have R minus Q. Right? What is R minus Q? R is 9. Q is also 9. So this is equal to 0. Your 8 is greater than 0. So what does it mean? It means your left subarray is greater than your right subarray. Obviously, your left subarray has 8 elements from 1 to 8. Your right subarray has 0 elements. That's what it's computing. This if condition is basically measuring if your left subarray is larger or right subarray is larger. So you got Q minus P greater than R minus Q, which means you'll go into this else condition here. What does the else condition say? So which line am I in? I'm in line 8. I'm on line 8. So I'll be on line 8, right? And what is it calling now? It will call, okay, let me just come down, scroll down a little, right? So now what it will do? It will call again. So it will call quicksort again. It will call quicksort again on array A with P equals to Q plus 1. So what is P? P will be equal to Q plus 1. My Q is 9. Q plus 1 is 10. Right? And what about R? R stays the same. What is my R? My R is 9. So it will call this quicksort algorithm. Now as soon as this quicksort starts, right, in my stack, look at what's happening on my stack now. So because this function called this function, on my stack, I'm going to store this function, right? All this information that I have of Q, A, 1, 9, right? And the fact that I am at line 8. This whole information goes onto my call stack. Again, remember that this is my call stack. Okay, remember that this is my call stack. So it calls this function now. Now let's see what happens with this function. So as soon as this function goes in, I'll check if P is less than R. That is not true, because P is greater than R, which means this while loop will never be entered into. Which means what happens now? Because this while loop has not been entered into, this will revert back. Right? This function will revert back. Now, which means it will revert back to line 8. So my line 8 has been executed. So it will go and run line 9. So what happens in line 9 now? So again, this function, see, I'm back. So this function has returned back. So my call stack is now again empty, because I'm back to the calling function. Now in this calling function, one thing is happening. R becomes Q minus 1. So what happens to my R? My R becomes Q minus 1. My R becomes 8. My P stays the same, because I came back to this function. Remember, this was a function that I was running. I called this function. I came back to this function. Okay, because remember, I have this while loop here. So when I came back to this function, my P remains the same, but I updated my R to Q minus 1. Okay, this is the fun part here. So what does this mean? This means now the effective array that I want to process, is only this subarray now. I don't care about the last element. because this has already been processed. Or in other words, what this function did was, this function processed the smaller subarray or the right subarray which was empty. Now after I have processed the right subarray, I go back to the calling function and I start processing the left subarray, which is a larger subarray now. Right? Now what happens here? Now again, let's compute Q here. What happens to Q now? Okay. So my pivot element is 8. So again my Q becomes 8. Okay. Now let's compare Q minus P versus R minus Q. Okay. So if this is my pivot element, so this is already taken care for. This is my left subarray and my right subarray is again null. Right? Because I don't have anything. So again, you'll see the same thing. Q minus P will be equal to 7, which is greater than R minus Q, which is 0. Okay. So because Q minus P is greater than R minus Q, you'll again go into the else condition. Now again, you are at what line? You are at line equals to 8. The stack is empty now. There is nothing on the stack. Let me erase everything on the stack. Because there is no calling function that is waiting to get finished. Right? So now from here again, I'll get a recursive call. Because what happens in line 8, I'll again call Quicksort. I'll again call Quicksort with A and Q plus 1. My P is Q plus 1. So what is my P? My P is Q plus 1, which is 9. And what about my R? My R stays the same. My R is now still 8. Right? So I'm calling this function. Now while I'm calling this function, again all these parameters go into my stack. So my stack will go in and say Q with A and P equals to 1, Q equals to 8 and R equals to 8. These are the values that I have. And it will also note that I am still at line 8. Right? If you notice, my stack has only one element now. Now here you will notice that P is greater than R. So because this while condition this while loop will only work when P is less than R. So this will immediately revert back. While reverting back, right? While reverting back, these values of P will remain the same. My R will become Q minus 1. My R will become 7. Right? Which means my effective array that I care about now is going to be only 1 to 7. So this will keep happening. This will keep happening now. See, we have started off with from 1 to 9 we have started. We went one step down. So on the call stack I pushed this. I called this function, this condition, this while condition did not meet, so I came back. Then I updated these variables because I have the while loop here. Remember, I have the while loop also here. I updated the variables here. I again called, I came back. Then I updated the variables again. Right? Then I'll update the variables again. Again, I'll go one step deep and come back. So if you keep following this logic, one thing that you'll notice is your call stack is always just one element deep. There is only, so in this case, if your array is already sorted, in the case when your array is already sorted, what you have here is using this function. Remember, using this function, when I use this function, this modified quicksort, which has both an iteration and these recursions. Okay, this is a very innovative implementation of quicksort. I always have only one element on my call stack for the worst case that we saw in the previous example, right? So which means now I might conclude that the space complexity is order of 1, which is not true, because I'll construct an example now where the space complexity, look at what this algorithm is doing. Intuitively speaking, what the algorithm is doing is very interesting. What the algorithm is doing is, suppose you have an array like this, right, with P and R. Let's assume this is my pivot element Q. Let's assume my pivot is here. So what the modified algorithm is doing in a nutshell, what the modified algorithm is doing is, it first processes the smaller subarray. It first processes the smaller subarray recursively, right? It processes the smaller subarray recursively. Once the smaller subarray is recursively processed, it goes to the actual function that called it. Because of this while loop structure. Remember, because of this while loop structure, first it processes the smaller subarray, right? This is the first step. Second step is it goes back to the calling function. It goes back to the original. It goes back to the original calling function. It goes back to the original calling function and updates variables. and updates variables in the for loop. Right? Look at this. What is this updating of variables? This updating of variables is nothing but line 9 here. R equals to Q minus 1 and also this part 7. P equals to Q plus 1. That's what the updating. That's what I mean by updating. It updates them, and then in the third step, it starts processing. In the third step, it starts processing the larger subarray. The larger subarray. Even while processing the larger subarray, it again, because it's a recursive thing, right? So first it'll try to finish this smaller subarray. Then it goes back to the calling function. Then it tries to process this larger subarray. Again, this larger subarray will be broken into two subarrays if you think about it. Even this larger subarray will be broken up into two subarrays, right? Again, amongst them there will be one which is smaller and one which is larger. Right? It will again process the smaller subarray first, goes back to the calling function and process the larger subarray. It will keep following these three steps recursively. It will keep doing these three steps recursively. So what will be the worst case of this algorithm in terms of space? So the worst case of this algorithm will happen when your pivot, worst case in terms of space complexity on the call stack will happen when the pivot breaks the array. When the pivot breaks the array into exactly two halves. Okay, so what happens then? Then this is my original array. This is my element Q. This is my element P. Sorry, this is my index Q. This is my pivot element, right? This is my pivot element, right? This is my R. If this is n by 2 and this is also n by 2, approximately n by 2, right? If both of them are roughly the same size, imagine if this array is of size 11, there are 5 elements here and there are 5 elements here, right? In such a case, there is no smaller. Both of them are of equal size. Then what happens now? So in this case, what happens is you will have a problem of size n. Let's assume then you will pick one of these two randomly, because let's assume this is also of size, because let's assume that the original array is of size 11. Your pivot element is exactly at the center, which means your left subarray has exactly 5 elements and your right subarray also has exactly 5 elements. So now you'll pick one of them randomly. Let's assume you pick the left subarray, right? Then a problem of size n will be broken up into a problem of size n by 2. So you'll call recursion on this. And again, let's assume it breaks down into exactly two halves. Now this subproblem also, let's assume, breaks it exactly into two subparts, n by 4 and n by 4. Then let's assume this is the smaller part. You keep recursing on the smaller parts, right? So this will call the whole thing on the array of size 1, n by 4, so on and so forth up to 1. So what is the depth of your recursion now? Because first you're calling with this full array. This is the smaller part, right? Let's assume this is of size n by 2. And now when I again run the pivot element, all of that, what happens? If this breaks it into n by 4, so on and so forth. So I'm recursively calling this. What is the depth of this recursion? This recursion depth is log n base 2. Right? We have seen this multiple times. We have seen this recursion tree. Right? So what happens is, if you have a situation, so if you have pivot elements, always breaking your arrays, breaking the array into equal halves, always, in each iteration, or in each recursion, basically. In each recursive call, if it's breaking up into equal halves, then what happens? Then your stack call depth, then your call stack depth, right? Then your call stack depth will be at most theta of log n. Because your array, which started off with 11 elements initially, or n elements, becomes n by 2 elements, and now this becomes n by 4 elements, so on and so forth till the time it becomes 1 element. And how? So this will call this, so this will call this, and so on and so forth. So you're starting off with an array of n elements, which is calling n by 2, which is calling n by 4, so on and so forth. So maximum depth of these calls will be log n. Because for every call, I'm going to add this. If I have n elements, I'm going to add that onto the stack. then n by 2 elements, whatever is the function call for that, then n by 4 elements function call, so on and so forth. So what will be the depth of this stack at most? It will be order of log n. So this modified algorithm that we have seen, in the worst case has theta of log n space complexity. Primarily because of the innovative way that it is using both iteration and also recursion, and it only recurses on the smaller subarray. But this is very innovative. The idea here is you have this iterative loop, right? And you only recurse on the smaller subarray always. Okay, and then update your variables here and go back into the iteration. The worst case of this will happen if your array, the worst case in terms of space will happen if your array constantly keeps breaking into halves, right? In that case, your maximum depth will be theta of log n, right? So this is a very, very interesting aspect of call stacks. This whole thing that we learned about space complexity of Quicksort, this is very interesting. Many people don't know this in detail. Even if you follow CLRS textbook, this is actually given as an exercise problem. This is not clearly explained in the textbook itself. And I have seen a lot of interviews at top-notch companies like Amazon, right? Top-notch companies like Amazon, Google, actually asking this question a few times. Because many people who do not understand Quicksort or call stacks will not be able to answer this. This is a very interesting question, and it's a very important topic also.